Welcome to section 14.2. We are continuing on with functions of two variables, and we're going to start getting into the calculus of things. And of course, when we're starting a calculus conversation, we have to talk about limits and continuity first. So to start off, we're going to let f be a function of two variables whose domain D includes points arbitrarily close to AB. Then we say that the limit as xy approaches AB of f of xy equals L. So notationally, there's not a lot changing about the limit notation. So instead of x approaching a as f of x equals L, we get limit as xy approaches AB of f of xy equals L. So we're just adding in that second variable. Now, the first thing that we're going to talk about, and that's the second part of this statement here, is the precise definition of a limit in 3D. This is something that you may or may not have encountered in your Calc 1 classes when you learned limits the first time. Some instructors cover it, some instructors don't. But we're going to look at the more precise and formal definition of a limit and see what that looks like in 3D, and then talk about some different approaches that we can take in limits in 3D in particular for Calc 3. So we say that the limit is equal to L if for every number epsilon greater than 0, this is a Greek letter epsilon, it's like a Greek letter E, there is a corresponding number delta greater than 0, so again, like a Greek letter D, such that if xy is in the domain and we have the square root of x minus a squared plus y minus b squared less than delta, then the absolute value of f of xy minus L is less than epsilon. So now, this is a very loaded statement. You probably didn't understand anything that I just said. That's okay. Let's break it down. So for every number epsilon greater than 0, there is a corresponding number delta greater than 0. Okay, so no matter what epsilon is, whatever number it gives us, there needs to be a delta that goes with that value. The relationship is what's described down here. So this expression right here, this form should look hopefully vaguely familiar, because this is basically a version of like the distance formula. This one is giving us the distance between the point xy and the point AB. So again, this is the distance between xy and AB. And remember, we have xy is approaching AB. So that distance between them should be shrinking because xy is approaching AB. So we're saying that that distance is less than delta. Okay, so if xy is in the domain and the distance between xy and AB is less than delta, so it's less than whatever this number is, then the absolute value of f of xy minus L is less than epsilon. This expression here, this is also representative of a distance. That's what the absolute value does. So we're taking the difference between f and L and then making it positive. So this is the distance between f and L. And again, as xy approaches AB, f of xy should be approaching L. That's the whole point of the limit. So we're trying to narrow in on exactly what the limit value is. Okay, so that's L. By shrinking the distance between the point AB and our arbitrary point xy, and that'll shrink the distance between the function and the limit. So let's take a look at these diagrams here. This might help us understand a little bit. So here we have the domain. we have the point AB in question. So xy is approaching AB. So you can see here I've got this little circular disk. The radius of this disk is delta. And you can see the point xy is here within this disk. So what this is saying back up here is the distance between xy and AB is less than delta. In other words, the distance between these 2 points should be smaller than this radius value. So in other words, the point xy should fall within this disk. Okay, so as we get closer and closer and closer to the point AB, the outputs of what we're getting, so like this is the output for xy right here, these outputs are getting closer and closer to the actual limit value. Okay, so and that's where we are approaching right here. So our point is within delta units of AB. The output is within epsilon units of L. Okay, so this is L plus epsilon, L minus epsilon. So we're within this region here. And the idea is, like, if we were going to make this like a game, you would pick an epsilon value. So you would say, okay, I want to know what the limit is. I want to know what L is. And I want to know it within like half a unit, within like 0.5. And I say, okay, so you want it within 0.5 of the actual limit itself. That's great. I'm going to find a delta that shrinks this close enough to AB that my point will still be within the 0.5. And then you say, okay, well, that's great, but I want you to be within 0.1 now. I want epsilon to be 0.1. So this shrinks in here and gets us even closer to L. And I say, that's great. I'm going to shrink delta, shrink this radius so that our point is in here and it'll fit within that range. And we can keep playing this game forever and ever. You can say, I want epsilon to be 0.0000001. And I say, okay, I'm going to find the delta that shrinks us close enough so that we can get to L. Okay? And we get closer and closer and closer and closer from both sides until we have pretty much narrowed in on exactly what L is. Okay? This is the idea of the limit, is approaching a value infinitely. Okay, and so now we're approaching a point in the domain, and the function is approaching L here on the z-axis. So in 3D, this is what's going on. So same idea, just in perspective a little bit. So we've got our disk down here. Our points would be within this disk, and their outputs would be within this range right here. Okay, so again, as we shrink epsilon, the acceptable range gets smaller, and so we start shrinking delta in order to make ourselves get closer to the actual limit value. And this is kind of the game that we play with limits. And this is, again, how we precisely define a limit. So the idea is when we are establishing deltas and epsilons, we don't want to go one by one, right? I don't want to say, pick this epsilon, let me find a delta. Pick this epsilon, find me a delta. Because we would do that literally forever. We need to come up with some sort of like rule that allows us to do this for all values, right? Because it says for every number epsilon. So what we will do, and we'll see this in an upcoming example, is we will try to establish a relationship between epsilon and delta so that when one shrinks, the other shrinks with it. And so it doesn't matter how small you make epsilon. It doesn't matter how close we get to L, because this disk will keep shrinking right along with it and get us closer and closer to the limiting value. So again, this is the precise definition of the limit. We're not going to do a whole lot with this, but we will be trying an example in a little bit and see kind of how this goes. Now, the issue that comes with doing limits in 3D. Back in Calc 1, when you learn how to take a limit, you have the limit as x approaches a, and then f of x approaches L. you're limited to only left and right, right? You just go right there, approaching from left and right to this value. The point doesn't have to be there. The issue in 3D is that we are no longer restricted to curves moving just left and right. We have infinitely many directions that they could come from. So if we're trying to approach this value, we could come at it from this way. We could come at it from this way. We could come at it from this way, from this way, from this way, and you get it, etc., etc. But there are infinitely many different ways we can approach this point now, not just from left and right. So this makes finding the limit definitively harder on us. So this property right here says that if f of xy approaches L1 as we get closer to AB along a path C1, and we approach L2 along a path C2, and L1 and L2 are not equal, so we got one limit along one path, we got a different limit along a different path. This tells us that the limit as xy approaches AB of f of xy does not exist, or DNE does not exist. So we can show that a limit does not exist in 3D by simply finding two paths that approach different limit values. Okay, so like when I approach along, this path over here, I get a height of 2. So that means the surface is approaching a height up here. But then when I approach along like this path over here, the value I get is like 1. So it heads down this way. And now there's like a disconnect between these two. So we would say that the limit does not exist. This makes it a bit harder for us to show that a limit does exist. So we'll talk about that in a little bit. But let's take a look at some examples of showing that a limit does not exist in 3D. So for this example, show that the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared does not exist. So what we need to do is we need to show that two different paths produce two different limits. Unfortunately for us, there's no limit to the number of paths we can choose. So there are infinitely many paths. As long as it's a function that approaches 0, 0, we can choose it. Now, for the context of this course, we're going to be fairly limited in the number of paths we're going to pick. We're not going to open it up to all possible curves, just for the sake of our practice. We will typically, if we're approaching 0, 0, we'll typically move along the axes first. So we'll try the x-axis, the y-axis. We'll try like linear functions like y equals x. We can try like parabolic functions like y equals x squared. So we stick with kind of the basic parent functions in here, just to get a feel for what this process is like. So let's go ahead and let's start working along the axes here. So first, approach along the x-axis. So if we're along the x-axis, that means that y equals 0. That's the equation of the x-axis. So we're going to have the limit of x, instead of xy, it'll be x0, because we're assuming that y is 0. Approaches 0, 0. And we'll sub in 0 for y. So we're going to get x squared minus 0 over x squared plus 0. So we get limit of x squared over x squared, which, of course, these can just cancel, and we're left with 1. So we get a limit value of 1 if we move along the x-axis. Okay, so coming towards 0, 0 along the x-axis. Our outputs are approaching a value of 1. Now, let's approach along the y-axis. So approach along the y-axis, which is the line x equals 0. So we get limit as 0y approaches 0, 0. So we get 0 minus y squared over 0 plus y squared. So we get our limit of negative y squared over y squared. We get some cancellation. However, there is a negative in there. So we got, as we approach along the x-axis, our outputs are heading towards 1. As we approach along the y-axis, our outputs are heading towards negative 1. So they're not going to the same thing as we come at it from two different directions. So what this tells us, so since f has two different limits, expand this out. Since f has two different limits along two different paths, the given limit does not exist. So since we have two different limits along two different paths, this limit does not exist, and that's all it takes for the limit to not exist. You could get the same path, the same limit value along every one of the infinitely many paths except one, and that's all it takes for the limit to not exist. So the trick is finding that one path, or coming to the realization that maybe the limit does actually exist. So let's take a look at another one. So we have the function xy over x squared plus y squared. Does the limit exist? So the last one said show that it doesn't exist. So it was assuming it didn't. This one it's asking us, does it? Does it or not? Well, let's try the axes again. So, because we're approaching 0, 0. So we'll do the x-axis, which is y equals 0. So we get limit as x0 approaches 0, 0. So we're going to get 0 over x squared plus 0, which is just 0. And then we'll try the y-axis. So that's where x is 0. So we get limit as 0y approaches 0, 0. That's 0 over 0 plus y squared, which is also 0. So we got the same value twice. So then the question is, does this mean the limit is 0? And the answer, in nice bright red, is no. No, very emphatically, no, it does not. I'll even put an exclamation point on there. It does not mean that the limit is 0. This means the limit might be 0. It could be 0, but this is only two paths, right? And there are infinitely many different paths we can choose from. All it takes is one of those paths to be different for the limit to not exist. This is just two. So yes, this does give an indication, like if the limit does exist, it's going to have to be 0, but this is not enough information yet. If we check something else, instead of moving along the axes, we're going to try moving along a different line. So along the line y equals x. So in this case, we're going to set this up as x and x, because again, y equals x, approaching 0, 0. So we'll get x times x over x squared plus x squared. So we're going to get, that's x squared over 2x squared, which simplifies to 1/2. So we got a limit of 0, a limit of 0, and then a limit of 1/2. And again, that one path produced a different limit, meaning that this limit does not exist. So different paths produced different limits. So the limit does not exist. Different paths produce different limits, so the limit does not exist. All right. So as you can see, being able to show the limit does not exist is a big part of our study of limits in 3D. The issue is we still have some of the same tools in 3D that we did back in Calc 1 to evaluate limits. The issue is if we want to definitively prove that a limit exists, then we're going to need to do a delta epsilon proof. So that's involving that precise definition of the limit that we talked about at the beginning of the section. So we're going to take a look at one example like this. And I mentioned earlier, this is not our primary area of focus because I think this general field of study is a bit beyond the scope of this class. But you'll have a couple examples like this on the homework just to kind of help you, it's going to ask you to fill in some blanks and to try to follow the logic of it as we're going through it. But again, our primary focus is going to be on evaluating limits directly or showing that they do not exist. But we do want to get you some exposure to this precise definition and how the flow of this proof would go. So here we have a limit as xy approaches 0, 0 of 3x squared y over x squared plus y squared if it exists. So the first thing we would do is we would check a bunch of paths and we would see what we get. So let me just make a note up here. So checking several paths. Oops, sorry. Checking several paths gives us 0. So if we check a bunch of paths on this, we would see that all of the paths give us zeros. And so this gives us the idea that the limit could be 0. So this indicates the limit might be 0. So we suspect that the limit is 0. In order to prove that the limit is 0, we need to set up the delta epsilon proof. Okay, so let's go ahead and do the setup here. So we're going to let epsilon be greater than 0. We want to find delta greater than 0 such that if, remember the distance between xy and 0, 0, so between xy and AB, if the distance between those two is smaller than delta, then the distance between the function and the limit, which we believe to be 0, should be smaller than epsilon. So we say x technically would be x minus 0 squared plus y minus 0 squared. So is less than delta. So if the distance between x, y, and 0, 0 is less than delta, then absolute value 3x squared y over x squared plus y squared minus 0 is less than epsilon. So again, this is the distance between the function and the limit that we believe to be the limit. Okay? If it's not actually the limit, then this method of proof would not work. We would have to reevaluate and try to find the appropriate limit value. Okay, so epsilon's greater than 0, it's some really small number, and delta greater than 0, again, an also very small number. If the distance between x, y, and 0, 0 is shrinking less than delta, the distance between the function and the limit should be shrinking less than epsilon. Again, that's us getting closer and closer and closer to epsilon. Another way to rewrite this, so we can say, or rather, we don't need absolute value on all of this. Everything here is either a number or squared, except for this y. So this would be 3x squared, absolute value of y, over x squared plus y squared, less than epsilon. This will kind of help as we're constructing our arguments here. So now comes the kind of the creativity of the proof, the logical leaps that we have to make to get what we want. Okay, so we're assuming that this is true. We're trying to prove that this is true. So to start us off, we're going to try to piece together something that looks like this. So since y squared is greater than or equal to 0, if we add x squared to both sides of this, x squared plus y squared would be greater than or equal to x squared. Right? If we just add the same thing to both sides, it keeps its inequality there. So if we divide both sides of this by x squared plus y squared, we get 1 is greater than or equal to x squared over x squared plus y squared. Which actually, I kind of want to put the variables first, so I think I'm just going to reorder this a little bit. So we'll say x squared over x squared plus y squared is less than or equal to 1. So same inequality, I just flipped it around. Okay, so we're getting actually pretty close already to getting a boundary on this. So you can say thus, if we take this expression and now multiply it on both sides by 3 absolute value of y, 3x squared absolute value of y over x squared plus y squared is less than or equal to 3 times absolute value of y. So again, I took this and this, multiplied them both by 3 absolute value of y. Okay, so again, it's not as big of a concern that you could come up with these steps, but more that you can follow the logic of them as we're doing it. So that gets us to here. So now this expression is this expression. And we're trying to show that this can be less than epsilon. If we can get that result, then we're done. Now, absolute value of y, if we think about some algebraic properties, that's the same thing as the square root of y squared. Right? Take the square and the square root, they undo each other, leaves you with the absolute value of y. Now, x squared would be a non-negative number, right? Greater than or equal to 0. So if I were to add an x squared in here, certainly this number would be greater than or equal to this number, right? Because I added this value, and it will always be 0 or more. And this value here, well, that we know is bounded above by delta. This is less than delta. So 3 times that is less than 3 delta. Now, the goal here is we're trying to find a delta such that this relationship holds for any epsilon greater than 0. And what I talked about earlier was this idea of we don't want to go one by one. I don't want to pick for this epsilon, it's this delta. For this epsilon, it's this delta. I want to come up with a rule or a relationship that will make this work. So if we look at what we have versus what we want, we have this. We want it to be less than epsilon. We have it less than 3 delta. So to make this less than epsilon, we want 3 delta to be epsilon, right? So let's let delta be epsilon over 3, and that would give us exactly the relationship that we want. So if we choose delta equals epsilon over 3, then this is going to give us the relationship we need. And again, this is why we establish a relationship like this, because now, no matter what epsilon value is given, we will have a delta that satisfies this relationship. Okay? Because delta is written now in terms of epsilon. So no matter what the epsilon is, no matter how small it gets, delta will shrink right along with it. So if we choose that to be our delta, then we get, so absolute value, 3x squared y over x squared plus y squared minus 0. So just kind of our standard setup here is less than or equal to this. So 3, instead of, we could write all these intermediate steps again, but we just had that written up there. That is less than 3 delta. Delta, we decided, is epsilon over 3. So we'll get to cancel those two. So we get epsilon. So what we just showed is that this distance, right, between the function and the limit is less than epsilon, which is exactly what we needed to prove. So in other words, no matter how close we get to 0, the function, the inputs will always be getting closer and closer to the point in question. So xy goes to 0, 0. Our function heads to the output of 0, okay, because their distance keeps shrinking, less and less and less and less as we go. So hence, the limit as xy approaches 0, 0 of 3x squared y over x squared plus y squared equals 0. And that would be the end of the proof. And this is a definitive proof, okay, that holds airtight, that definitively shows that the limit is equal to 0. So it is true that all infinitely many paths would have produced a 0, but we can't do that by testing one path at a time. We have to prove it using a method like this. Now, this, of course, is not the most efficient method for showing that limits exist. Sometimes it's our only option, but in calculus, we often like to talk about continuity. Continuity is going to really help us out here. So a function f of two variables is called continuous at a point a, b if the limit as xy approaches ab of f of xy equals f of ab. So this definition for continuity is basically the same as it is in Calc 1. It's the idea that the limit exists, the function exists, and they are equal to each other, right? It's kind of those three criteria you hear in calculus. The limit has to exist as we approach AB. The function has to exist at AB, and whatever those values are, they need to be equal to be continuous. The nice thing about continuity here is if we know that the functions are continuous, we can use the properties of limits similar to single variable calculus. So as long as we know the functions are continuous, we can use things like algebraic manipulation and simplification to help us solve limits rather than using delta epsilon proofs every single time. So let's take a look at some examples here. So evaluate this function. So we'll put a little note right here. So note, so this function is a polynomial. So it is continuous everywhere. So just like in Calc 1, polynomials are continuous everywhere. So we can simply use direct substitution to evaluate. So this function is a polynomial, so it is continuous everywhere, so we can use direct substitution to evaluate, meaning we don't have to use that delta epsilon definition anymore. We can simply just plug in the 0.12, just substitute in those values for x and y, and we're going to get 1 squared times 2 cubed minus 1 cubed times 2 squared plus 3 times 1 plus 2 times 2. So that's 8 minus 4 plus 3 plus 4, which is 11. So much nicer, so much faster than using that alternative method. And again, this only works because of continuity, because it obeys those properties. For the next one here, where is this function continuous? X squared minus y squared over x squared plus y squared. So this one, we know that the function doesn't exist at 0, 0, right? Because that would give us a 0 in the denominator. So this is discontinuous at 0, 0. Now, this is a rational function, and rational functions behave like they do back in algebra and Calc 1. So we can say, since f is rational, it is continuous on its domain, which includes all values x, y, except 0, 0. So if we were going to write its domain, we would have D is the set of points x, y, such that x, y is not equal to 0, 0. Something like that. So we see that its domain is all of R2 except for 0, 0. Right, so this is all of R2 except 0, 0. Now, in the example down below here, we have the same function. However, we've now made it piecewise, and we've said, okay, I know this function is not continuous at 0, 0, so we'll say, let's use it everywhere except 0, 0. When we are at 0, 0, I'm going to let the output be 0. Because the idea is, this function doesn't exist there. Maybe there's just a hole there, and we can try to plug the hole by just letting the output be 0 at that point. And we need to figure out if that works. Okay. So we can say, so here, g of xy is defined at 0, 0. So this is already a step above the last one. However, we have actually looked at this function before, the x squared minus y squared over the x squared plus y squared. We found the limit of it, right? Or actually, more to the point, we showed that its limit did not exist at 0, 0. This is one of the examples we did a little while ago. So we can say, however, we have previously shown the limit approaching 0, 0 does not exist. So it is still discontinuous at 0, 0. So we can conclude thus it is continuous because it's still a rational function everywhere else. So it's continuous for all of R2, and I'll fill that in by hand. So all of R2 except 0, 0. So again, that's all of R2 except 0, 0. And that brings us to the end of section 14.2. That is our introduction to limits and continuity in the third dimension. So we're really getting into the thick of the calculus now. And this is going to continue as we head into derivatives and all that good stuff in the upcoming sections.